Good afternoon, everybody. We are Team 3, and today we're going to present our project on Bluetooth-enabled lung function remote monitoring. So the purpose of our project is that we want to develop an application that will allow for remote management of a patient's pulmonary function through an application that utilizes Bluetooth-enabled PEF meters, also known as spirometry device. So to start off with some objectives that we're going to discuss is that we're going to discuss the impact of COVID-19 on lung function and spirometry. We're also going to analyze the current and future workflows involving remote and home healthcare, discuss the development of an application as a solution for challenges in monitoring lung function, and we're going to wrap it up and describe the future state and potential impact. So COVID-19 has massively impacted the global healthcare system over the past 2 years. Healthcare has been forced to adapt to be on the go, and remote and home healthcare has received renewed emphasis due to the nature of the pandemic. And along with the nature of the pandemic, due to the extent of the virus's ability to spread and damage lung function in a person, there are limited avenues to track spirometry of a recovered COVID-19 patient. And so there is a need for healthcare providers to manage and monitor patients' lung function remotely. So as a preview to talk about our topic, we're going to review a patient case first. So WM is a 45-year-old female with a past medical history significant for chronic obstructive pulmonary disease, also known as COPD for short, hypertension, atrial fibrillation, diabetes, and dyslipidemia. She was recently exposed to COVID-19 back on October 10th and was hospitalized in the ICU. She was recently discharged on November 25th. Some recent labs regarding her lung function, we have her forced expiratory volume, or FEV1 for short. Prior to admission, about a month before she was exposed to COVID-19, she went for a regular healthcare visit, and her lung function, her FEV1, was about 60%, which based on the GOLD guidelines, this is considered to be moderate. And then when she acquired COVID-19, when she was recently acquired COVID-19 back on October 10th, and when she was hospitalized, they measured her FEV1 to be about 40%. Now that she's recovered and she was discharged, they decided to look at her lung function again, and they found that it was at 45%. So now that she is being discharged, she's going to be referred to her primary care physician, where it's up to them to monitor her lung function. This is not only important because of her recent COVID-19 recovery, but because she also has a past medical history of chronic obstructive pulmonary disease, or COPD for short, it's very important that her primary care physician monitors her disease progression. So there is a need for this because it's essential for providers to have reliable spirometry data in order to monitor lung function. It's also important in that remote management allows for clinicians to monitor multiple patients simultaneously. The reason being is that with COVID-19 being an airborne disease, with the virus's potential to inflict a large number of people, it's vital for patients to receive care in a way that does not expose other individuals as well.
As highlighted in the problem statement, the current workflow involves the patient actually using the spirometer and sending the data to the provider either over email, over a phone call with the staff, or over messages. And that's been highlighted very well in the current system workflow. So the future workflow is the workflow that we plan for the application. And this workflow involves using an automated application to handle the communication part. So the Bluetooth low energy device the patient uses gets an application with it that they can use on their smartphone. And the patient can use the spirometry device and have the data automatically transferred over to the cloud database, where the provider can look at it immediately or on a day-to-day basis, and that evolve into better quality of care and better clinical decisions are made by the provider as, in case there is a reduced peak flow in coming days, they can observe that and they can request the patient for a visit. So the application or the system itself has two pieces. There's a hardware piece where a Bluetooth low energy spirometer is involved, and the software, the application piece where most of our development has taken place. The hardware of choice is Mir Smart One. It's a pocket-sized Bluetooth device. It's designed to be used with COPD, asthma, and respiratory problems, but it has been found to be quite effective in tracking um, reduced lung function for patients who have recovered from COVID. And these values are very important for a pulmonologist. It meets the FDA requirements, so it's the ideal device for us to connect to the cloud and then to the providers. Here's the high-level system architecture of the software. On the left-hand side, you'll see the patient pulmonology application. This is the application that's installed on a patient's smartphone that connects with the Mir Smart One, the Bluetooth low energy spirometer. And this application also guides them through the entire session. What's interesting about this system architecture is it's highly available, scalable, and being in line with the latest cloud trends. It's a serverless application model. All the data exchange happens over the API, which is serverless, and the backend function, which connects eventually to the database right here. All the authentication and authorization is handled by an identity server that's present over here. And there's a patient authentication piece and a provider authentication piece. The provider authentication, of course, having control over the visibility of all their patient data in case they need to make a call. As far as system security is concerned, of course, there's patient identifiers involved in the database, and we have taken several measures to overcome some of the issues with having the data offsite from provider's location and making sure it's HIPAA compliant. They made sure the data at rest in the database and in object storage is encrypted using SHA 256. That's a 256-bit encryption. It's highly secure. All the data in transit is encrypted using TLS 1.2, and that's a more secure encryption method than SSL that's available on regular web applications. An application does use separate instances of identity server and lung function records as highlighted in the system architecture in the last slide. Reliability. So the system, as mentioned earlier, the system does use state-of-the-art system application model. This allows for infinite scalability and high quality of service during peak hours. System application model is strictly on-demand pricing, so you pay for what you use, but since it's a functional model that allows for extremely cost-effective and flexible IT infrastructure, and the application itself is installed on a well-architected cloud service that allows for operation excellence, highly high security, reliability, performance efficiency, and cost optimization.
So some of the constraints we'll face within this project are going to be just definitely making sure that we have a high quality user interface and just making sure that users have a relatively good experience when they're using this. Also ensuring that there's a continuity and monitoring and providing care to these patients. Training and making sure that patients and providers and clinicians are able to utilize this project and product in an efficient way to ensure that the experience is overall a good experience. Making sure that clinicians and providers are comfortable with having this sort of off-site data collection and their comfort in analyzing that sort of data. The patient's overall ability to navigate and utilize the product, which goes back to training and making sure that the patient is able to utilize it well. And then the consistent adaptations that are forced within healthcare just due to the unknown. So just consistently being able to evolve and adapt to what's going on at the current time. So the overall budget for our project was about $54,500. The largest total came from consulting, and this is just an overall breakdown of our budget and analysis. So with this, there's a good amount of risk to consider, especially for a project of this magnitude. The delay in project phases and the overall production of this project and kind of going from one step to the next at a timely manner. That was mitigated by having a project lead and using the Kanban to kind of manage tasks and overcome that barrier or potential barrier. A lack of communication, which was mitigated through having a project lead and resolving issues through kind of a monthly or a weekly sprint, going through issues and making sure that everything worked out. And inadequate testing prior to going live. The systems engineer just needs to conduct unit testing and system testing. Bug tracking should be brought up in the weekly sprints to making sure to go over any potential issues, any potential overall problems that might need to be tackled before they become bigger issues and snowball. Here's our overall organization chart. We'll go into some more of these individuals and their responsibilities just based on their roles. But this is the kind of hierarchical chart with Hunter Live being the project lead, and we'll go into each individual in the next couple slides. So like I said, Hunter Live is the project lead. The largest thing is just mitigating risks, monitoring for project progress, controlling costs, and making sure that there's effective communication. Heidel Veer is the systems architect, designing IT stacks and its overall components and requirements. Fisher Pope is the database engineer, designing the database and data fields for capturing pulmonary data, creating ER diagrams, creating SQL scripts for database deployment. Bill Chaston is the HCL engineer. He's designing user interface for acceptable application usability, designing user experience and application workflow, designing use case diagrams. Samantha Walker is the business analyst, validating requirements with end users and run user acceptance tests with focus groups and experts, running technology acceptance tests using the surveys from the focus groups.
Here are the responsibilities of other staff members. Our system analyst plan the IT resources as per the budget. Backend engineer create the Terraforms to write the API functions and develop API. Front-end engineer develop React and React Native front-end applications. They both work together to implement and test API connectivity. System engineer tests system functions, discover bugs, and resolve pending issues. Going to the estimated timeline, we are following agile methodology for the project execution. Project will go through 4 to 5 weekly sprint cycles. Any changes introduced during the executions are added to the additional development sprints. Milestones are broken down into tasks. So the first task is system architect design, where IT stacks and requirements are designed by the system architect. Also, simultaneously, database engineer works on designing the database and data fields as per the pulmonary data. After data modeling, HCI engineer designs the user face and user experience as per the use case diagrams. And then the business analyst validates the user requirements with the end user and completes the system validation task. After that, system analysts need to submit the IT resource plan as per the budgeting, and database need to be deployed. Before API integration, backend engineer and front-end engineer need to work together and finish the API development and front-end application development so that the API connectivity is tested. Before the project goes live, application testing, user acceptance testing, and technology acceptance testing are run several times in order to make sure the application is effective. Here are the outcomes of the project. We had completed all the milestones involving designs, development, and integration for the successful development of the application. We have gone through several rounds of testing and debugging. We had a continuous tracker for bugs. We used Jira tracking, so we fixed them as we found them by adding to the weekly sprints and the additional task. User acceptance testing and technology acceptance testing were conducted through survey with a focus group containing around 20 patients and providers. 10 to 15 questions were asked, and the scores from the surveys were used to measure the rate of acceptance. If the values were below certain threshold, we considered it as technology acceptance failure. Same was done with the user acceptance testing too. Future state, we wanted to integrate the application with the EHR using HL7 and other interoperability tools. One of the request items from the user acceptance testing was self-reported system tracking. The provider wants to know the symptoms like cough, aches, rashes on daily basis, and another piece which they requested in the user acceptance was physical activities tracking, so that the providers can prescribe the physical activity needed for the proper lung function. Next to the questions.